Hello, and welcome back to the Actuate YouTube channel. In this video, which is the second video in our probability series, we're going to be going over sets, unions, intersections, Venn diagrams, and sample spaces. Before I get started, here at Actuate, we offer free tutoring for probability and financial math. While we're geared towards the Society of Actuaries exams, if you're having trouble in probability or financial math coursework, please do not hesitate to click the website link in the description of this video. It's going to be right at the top, and if you're looking for aid for Society of Actuaries exams, link will also be there for the same thing. I decided to start today's explanation with an example, and it's sort of a comprehensive example of every topic that we're going to be going over in this video. So let's start with what I have here. I started by defining a sample space, and the sample space in this example is going to be all integers from 1 to 12. So we're going to have 12 separate numbers, 1, 2, 3, 4, all the way up to 10, 11, 12. And I've defined two sets. Set A is the numbers 1, 3, 5, 7, and 9. And set B is the numbers 1, 2, 3, 4, 5, and 6. And so I have a bunch of questions down here, which we're going to get to. But to start off, I want to start by analyzing the problem, seeing what we have going on, and then as we go down, I'm sure a lot of these terms may look a little bit foreign, or you might not have seen them before. And as we go down, I'm going to make sure to explain each and every one of them, what they mean, how to solve for it, and then at the end of it, we're going to do a Venn diagram visualization, which is going to help us in the problems below. So let's get started. Over here, we have A and then this U and B. So what does that mean? And before I define it, let's see what we have going on. So we have two sets, like I said before. Set A is these 5 numbers, set B is these 6 numbers, and they're asking here A, U, B. So let's define what this means before we calculate for it. So this right here is what mathematicians define as a union. And what a union means in this case is we're going to take all elements. And to define elements, for those who aren't familiar, in set A, we have 5 elements. Element 1 is the number 1, element 2 is 3, element 3 is the number 5, element 4 is the number 7, and element 5 is the number 9. And the same thing goes for below. In this case, we have 6 elements, and element 1 is 1, element 2 is 2, and we go so on to 6. So to calculate for a union, we're going to take all elements that appear in either set. So looking at what we have here, we have in set A 1, 3, 5, 7, 9, and in set B we have 1, 2, 3, 4, 5, and 6. So if we're going to look at this comprehensively, and we're going to calculate, right, A union B, what it's going to be equal to is everything in set A. So 1, 3, 5, 7, 9. And then I'm going to add the elements in set B that haven't already came up in set A. And for the first element, 1, which appears in both sets, I'm not going to write it a second time. I'm just going to write elements that we have not had. So the 3 new elements now are 2, 4, and 6. And so to write it in numerical, or I guess just from lowest to highest order, we would have 1, 2, 3, 4, 5, 6, 7, 9. And so this right here is equal to A union B. So going down now to this, what do we have here? If A, U, B is a union, and the union means everything that appears in both sets, this upside down U, well, this is what we call an intersection. And the intersection, well, with no S, the intersection is calculated by taking all elements that appear in both sets. So recurring elements. So I'm going to remove this up here and drag this up just to save space. So looking at our two sets, we're going to find which elements are in both. So 1, we have 3, and we have 5. And 2, 4, and 6 are only in set B, and 7 and 9 are only in set A. So A union B is, in this case, going to be equal to the first 3 odd integers. So 1, 3, and 5. That is equal to A intersection of B. So just general terminology, right? Union, intersection, union, think of like unity. You're unifying the sets, you're bringing them together, and then intersections is where elements intersect with each other. So they're in both sets. Seems straightforward enough. It is very intuitive in terms of language, and you know, it's sort of just looking at the two sets, comparing the similarities and differences and intersections and unions, and it all just takes care of itself. So now we have A apostrophe and B apostrophe. What does this mean? So the apostrophes in this case, they are complements. What a complement is in a sample space, we defined as our sample space, right? 1 to 12, so every integer from 1 to 12. And when we're calculating a complement, we're going to take the sample space and keep in mind the sample space is defined from 1 to 12, which means we have 12 elements. And from that, we are going to subtract all elements in set A. And we're going to do the same thing for B. So if we're calculating for B complement, take sample space and subtract elements in set B. In essence, A complement is everything in the sample space that doesn't include whatever is in set A, and B complement is everything in the sample space that doesn't include set B. So if we're going to calculate this, how are we going to do that? Well, we're going to take the sample space, 1 to 12, and we're going to remove everything in there from set A. So we're going to have to remove the first 5 odds to calculate A complement. So in this case, we're going to have 2, 4, 6, 8, 10, 11, 12. And we're going to have 7 elements there, which checks out because we have 12 elements in the general sample space. 5 of them are in set A, and the remaining 7 are the complement. What is not? For set B, the complement is going to be everything subtracted from the first 6 numbers. So B complement is equal to 7, 8, 9, 10, 11, 12. This is A complement, and this is B complement. So moving down now, I want to start calculating some probabilities, because that's the name of the game. We need to calculate the probability of something happening and the probability of something not happening. So I have 2 examples here, and before we calculate them, I think it's actually going to be easiest to calculate them through a Venn diagram visualization of everything we've just seen. This may seem a bit foreign. It definitely was to me when I was learning this for the first time, but a Venn diagram is actually extremely helpful for calculating these sorts of problems. Well, first of all, I should define what's going on here. So this big box is the sample space. Everything inside of the sample space is the elements. So within this box, whether they're in, this circle, the intersection of the circles, this circle, or maybe even on the outside, wherever it is, you are going to see every element of the set. So 1 through 12, all of them will be written in this box somewhere. I'm going to define this circle as A, and I'm going to define this circle as B. So what does this mean? Over here, everything that I have shaded is going to be all the elements of set A. So the numbers 1, 3, 5, 7, 9, they're going to appear in here somewhere, either just in A or the intersection of A and B. So erasing this and going to B, similar logic is applied. Oh, what the heck did I just draw? Okay. Similar logic is applied here. Any element in set B, which we have defined as 1, 2, 3, 4, 5, and 6, is going to be in the just B section or the intersection of A and B. And then we do have some elements that were not present in either set, but are still in the sample space, and you're going to find them somewhere out here. So let's get to defining. I think it's easiest to start in the middle, actually. So in here, I'm going to write all the numbers or all the elements that have appeared in set A and set B, which we've actually defined as the intersection, which is this. So going back to our intersection, we've determined that A intersect B. That's the sort of terminology that's used. It's these three elements, 1, 3, and 5, because 1 appears in both sets, 3 appears in both sets, and 5 appears in both sets. So in here, I'm going to write the numbers 1, 3, and 5. In the first set, there are 5 elements, 1, 3, and 5, appear in both sets, so just 7 and 9 are the integers or the elements that appear in only set A. And by similar logic, 2, 4, and 6, which are the non-circled numbers, which are the ones that are in both sets, those are the ones that are just in set B. So 2, 4, and 6. And then numbers that aren't in here going up to 12, so 8, 10, 11, and 12. Those are still in the sample space, but they aren't in either set, and they're definitely not in the intersection of both sets. So this is sort of the visualization of what we just did. We have 7 and 9 that are in just A. We have 1, 3, and 5 that are in both sets. We have 2, 4, and 6 that are in just set B. And then 8, 10, 11, 12, which are in the sample space from 1 to 12, but in neither set. Coming back to this, P bracket number is in set B, close bracket. What does that mean? This is just probability notation for actually the calculation of probability. So all that this is asking is, it's asking us to calculate what is the probability that a number in the sample space is actually in set B. So go into our Venn diagram and looking at set B, which we have here, I can see that 1, 2, 3, 4, 5, and 6 are in set B. So we have 6 numbers. And the way that you calculate probability, the formal definition of probability is number of desired outcomes divided by the number of total outcomes. It's a bit wordy, but in essence, think of it like this. If you want to calculate the probability of flipping heads on a fair coin, which we all know is 1/2, there are 2 outcomes, heads and tails, and the desired outcome in this case is heads. So heads or tails would be equal to 1/2, 50%, or 0.5 in probability notation. We define everything as a decimal and the total sum of probabilities to be 1, sort of similar to percentages. In this case, we have 6 desired outcomes. That's the amount of numbers in set B. And we need to calculate the number of total outcomes. And that's just going to be all the elements in the set. 6 of the outcomes are in set B, but we have 12 total outcomes. And those outcomes are going to be all of the integers from 1 to 12. 1, 2, 3, 4, 5, 6, all the way up to 10, 11, 12. And if we wanted to, put this into a decimal form, we would just get 0.5, which checks out. We have 1 number, 2 number, 3 number, 4 number, 5 number, 6 number, 6 elements inside set B, and then there are 1, 2, 3, 4, 5, 6 elements that do not belong to set B. 6 over 12 equals 50%. Checks out pretty good to me. And then I'm going to ask, what is the probability that a number is not in set A or B? And by the same logic that we used before, the number of desired outcomes are over here. They're the numbers that are in the sample space but are not in either set. 8, 10, 11, 12 makes 4 numbers, or 4 outcomes. Still 12 total outcomes. There are 8 remaining inside of the circle. And that's going to give us a fraction that's simplified as 1/3 and a probability of 0.33. So that's pretty much all the terminology that you could be asked on a Society of Actuaries style exam. You have unions, you have intersections, you have complements, and you have that sort of general probability notation. All elements are part of a sample space, and they could be part of a set. So going down to some examples now, I have 2. The first one is a word problem, and now instead of a sort of set amount of numbers in the set, we have probabilities. And the question says this: an individual could be sick with the flu, COVID, both, or neither. The probability that an individual has the flu is 0.6. The probability that an individual has both the flu and COVID is 0.1. And the probability that an individual is not sick at all is 0.2. What is the probability that a randomly selected individual is sick with COVID? That's a lot of words, that's a lot of numbers, and the best way to start is just by breaking this down into the simplest terms possible using the notation and language that I just explained earlier. So what's jumping out first to me is this line here. The probability that an individual has the flu is 0.6. And using the notation that we had before, we could say that probability that someone has the flu is equal to 0.6. The probability that an individual has both the flu and COVID is 0.1, which, using the terminology we had before, would be this: flu intersection with COVID is equal to 0.1. And finally, the probability that an individual is not sick at all is 0.2. So in the notation from before, this would be equal to the union of A complement and B complement. So anything that isn't a part of both of the sets. And actually, now that I'm looking at it, a much simpler notation here would actually just be this: calculating the probability of A union B and then taking the complement of that. So the probability of that is defined here by 0.2. And they're asking, what is the possibility that a randomly selected individual is sick with COVID? So we have our information simplified down as much as possible. The natural step here is actually to go right back to the Venn diagram and draw everything out. So it would look a little something like this. I'm going to take the box just like before, and the box is going to be the sample space. It's going to be these selected individuals from this sample size. I'm going to draw two circles again. Oh, still on the eraser. I'm going to name the left circle flu. I'm going to name the right circle COVID. And anything that isn't inside of these two circles is going to represent people not being sick at all with either. And we could see that by 0.2. I'm going to put this on the outside. Usually it goes in the bottom right, but you can put it wherever you want. You can put it on the top, you can put it on the bottom left, you could put it anywhere as long as it is not inside of those two circles. Going back here, we see that the probability that someone has the flu, which is right here, is 0.6, which is good. We know what this whole circle is equivalent to. However, we don't know how it's sort of distributed between just the flu or people that have the flu and COVID. So we can't fill anything in there just yet. But this line right here, probability of flu intersection with COVID, which means people that have both diseases, is 0.1. And that right there is a very valuable piece of information because we could stick it right here, 0.1. We can actually go back to the probability of the flu. Probability of someone has a flu is 0.6. And we know that 0.1 of those people out of the entire sample set have both COVID and the flu, which means the residual 0.5 is going to go on the left. And if you're not sure what I did there, it's just this. This whole circle, we could name this portion 1, and we can name this portion 2. Portion 1 is just for people that have the flu, and portion 2 is for people that have the flu and COVID. This whole circle entirely is people that have the flu. It doesn't matter if they have just the flu, it doesn't matter if they have the flu or COVID, and COVID. They're sick with the flu regardless. So it said in the problem that the probability that an individual has the flu is 0.6. We were told that the probability that they're sick with the flu and COVID is 0.1. So in order to fulfill that 0.6, the remaining 0.5 is going to go in just the flu. We have 100% of people. The law of total probability, which is a general probability law, just says that all probabilities in the sample space, unless otherwise stated, have to equal 1. With these numbers, we are just going to subtract them all from 1 to determine what goes in this column, which is just people that have COVID. So I'm going to take 1, I'm going to subtract the 0.5, which is people that just have the flu. I'm going to subtract 0.1, which is people that have flu and COVID, and I'm going to subtract 0.2 over here, which is people that have neither. And the result of this is that I get 0.2. That 0.2 goes in here, and everything checks out. 0.5 plus 0.1 plus 0.2 plus another 0.2, that equals 1. It checks out. So we have our Venn diagram completely filled. And now going back to the actual question, they're asking, what is the probability that a randomly selected individual is sick with COVID? We're just going to go right here. This is the COVID circle. We have 20% of people that are sick with just COVID. We have 10% of people that are sick with COVID and the flu. And they're all sick with COVID, so we're just going to add them up. So the 0.2, which is just people that have COVID, the 0.1, people that have COVID and the flu, is going to equal 0.3. So there's a 0.3 or a 30% chance that a person that is randomly selected is going to be sick with COVID. One final example for this video. This actually is derived directly from the SOA public question bank. This is question number 3, and it states this. You were given the probability of A in union with B is 0.7, and the probability of A in union with B complement is 0.9, and they want you to calculate the probability of A. So I'm going to go and use the same process that I used before. I'm going to write down what I know. I'm going to use a Venn diagram, and we're going to figure this out together. So probability of A union B is equal to 0.7. I'm going to rewrite that over here. And we know that the probability of A in union with B complement is equal to 0.9. And they're asking for the probability of A. So what do we got here? Let's draw the Venn diagram. I'm going to name this circle over here. Oh, what the heck just happened to that circle? All right. So I'm going to name this circle here A. I'm going to name this circle here B. And I'm going to go back and see if sort of anything that I had here could be of any use. So I got probability of A union B is equal to 0.7. So what's that telling me? Well, it's telling me that anything that is in set A or in set B or in both is equal to 0.7. So both of these circles, including their intersection, is going to be equal to 0.7, which means everything on the outside is going to be equal to 0.3. So we already got a big piece of the puzzle solved. Let's see if the second piece of information could give something. They're saying that the probability of A in union with B complement is equal to 0.9. Interesting stuff. So what is that saying? Well, we have the probability of A. So set A is denoted by this. This whole circle is A, so it's anything that is just A or A in union with B. And then they're saying that this set A is being put in union with the set B complement, which is everything that is not B. So this is B, so we can't put it. This is B, so we can't include that in the set. The intersection of A and B is included in set A, so we're going to keep that. But what is new is everything on the outside. So all of this is equal to 0.9. We already know this is 0.3. We're going to actually, as a result of that, know that this square right here, this circle of just A is actually going to be 0.6, which means that this residual B, which is the only thing left, is going to be 0.1. The way I got that was I took 1, which is the sum of everything, and I subtracted the 0.9 from it. And as we stated before, the 0.9 is everything in A in union with everything that B is not, B complement, which is the circle A and everything on the outside. So removing my scribbles to get an easier Venn diagram to write on. We know that on the outside is 0.3. We know that just B is 0.1, which means that this whole circle, we don't know how it's divided, but the probability of A is 0.6, and That is what they're asking us for here. That's going to be our answer. That's all I have today for this video. I am going to release a video as a follow-up to this where I'm going to go over a more complex example, but I figured that was a bit more difficult and it deserved its own video. So all there is for today. Thank you so much for tuning in, and I will see you in the next video.